Cats in Latent Space, an exploration in 5 acts. How do AI image generators such as DALL-E, Midjourney, Stable Diffusion, or Adobe Firefly turn text into images? They're all based on a type of neural network called a diffusion model. In this video, we're going to explore how diffusion models work. Along the way, we'll meet 3 characters, Vi, Una, and Cliff, who represent different parts of the model. In 5 acts, you will see how amazing the diffusion model is. Our story begins with cats. Act 1. Scribbles. Suppose you have a friend Vi who's really good at drawing cats. You can scribble a few lines suggestive of a cat, and Vi will turn that into a beautiful, detailed cat image, like this, or this, or this. Although your scribbles are only a few lines, they express the essence of the image you want. Vi pays close attention to your lines and depends on them for guidance. Any small change to a line results in some change to the image. Each scribble is a latent description of a cat. Latent means hidden, potential, or undeveloped. You scribble a potential cat, and Vi turns this into a detailed cat image. But if your scribble doesn't describe a cat, Vi won't know what to do with it. Act 2. Manifolds. Imagine if instead of scribbling a latent cat description, we could describe a cat by writing down 3 numbers, X, Y, and Z. Then every latent cat would be appointed those coordinates in a 3-dimensional latent cat space, like this, and this, and this. When your friend Vi was learning to draw cats, they studied thousands of cat images. After sampling enough points, they saw that the points lie on a complex surface called a manifold. Any point on this surface is a latent description of a cat. Nearby points describe similar cat images, and points slightly off the surface describe cats that are slightly off, while points far from the surface do not describe cats at all. Perhaps your friend Vi has also studied how to draw trees. Trees form another manifold in a different part of the latent space. If Vi knows how to draw many different things, they have learned many manifolds. But let's get back to cats. What if you want to ask Vi for a cat, but you can't quite get to a point on the manifold? As long as you can come close, your other friend Una will map the point onto the manifold for you. Una is smart enough to figure out which spot on the manifold you are aiming for, and Vi will generate a cat from that. Let's look at this again. Your latent cat description doesn't have to be perfect. You can give what is called a noisy description, and Una will correct for your lack of precision because Una knows what cat description should look like. In other words, Una knows the latent space of cats, while Vi knows how to map latent cats into real cat images. Una's ability to map noisy latent cat descriptions into good ones turns out to be extremely useful. Act 3. Noise. We pretended that just 3 numbers were enough to describe a latent cat, so we could visualize the cat manifold as a 3-dimensional surface. But in reality, many more numbers are required to describe a cat, around 4,000. This means the real cat manifold lies in a 4,000-dimensional space. Such a space is hard to visualize directly, but we can offer an artistic impression of its complexity. As before, Vi will map points in this latent space into points in image space, meaning pictures of cats. The cat manifold lying in this 4,000 dimensional space is equally hard to visualize, but we can again offer an artistic impression. We use the term noisy to describe points that are not quite on the cat manifold. Their coordinates are imprecise. Una's job is to remove the noise and get us to a point on the manifold. Una cannot remove all the noise in a single step. Instead, Una removes a little noise at a time, resulting in a series of points in 4,000 dimensional space that come closer and closer to the manifold. If we asked Vi to generate images from these intermediate noisy points, what would we see? Far from the manifold, the images don't look like anything at all. You might say that they are pictures of latent noise, with maybe a tiny bit of cat flavor mixed in. As Una removes more of the noise from the latent description, moving the point closer to the manifold, the images Vi produces become clearer and clearer. Remember that the denoising is taking place in 4,000 dimensional latent space, not in the image directly. But denoising the latent space coordinates lets Vi produce increasingly clear images. We can use Una's ability to move a noisy point onto the cat manifold to generate an infinite variety of cats. All we have to do is shift our starting point by a little bit in a random direction. The shifted point is still far from the manifold, so Vi produces an image of latent noise. But Una will take the shifted point to a slightly different spot on the manifold than before, and this causes Vi to produce a different cat image. Since our initial point can be shifted in any combination of 4,000 directions, that makes a lot of cats. Act 4. Words. How do words give rise to images? In particular, when we say a cat lying on its side, how do we end up with this image? Latent images of cats lying on their side occupy a particular region of the manifold. We're going to go back to our three-dimensional manifold for simplicity's sake, but don't forget that this is actually a 4,000 dimensional surface. So what we're asking is, how can words guide Una to a desired manifold region? Una receives guidance from another friend of ours, Cliff. Although we are meeting Cliff last, he is actually the beginning of the story. Cliff studies image caption pairs, about 400 million of them taken from the internet. Cliff's job is to find correlations between the captions and the images. For example, if a caption contains the phrase, "a cat," then the image likely contains a furry thing with pointy ears and whiskers. Conversely, if the furry thing in the image is oriented a certain way, then the caption likely contains a phrase such as lying down or on its side. Cliff develops his own complex representation of the features found in the captions, the features found in the images, and the correlations between them. This representation is called an embedding. Using this embedding representation, Cliff is trained to predict whether a given caption goes with a given image. When Una is learning to map points onto the manifold that Vi constructed, she's also given Cliff's embeddings, containing information about the textual descriptions of the images. Una associates these embeddings with their manifold points. We can think of this as painting the surface of the manifold with Cliff's embedding patterns. In other words, the images determine the shape of the manifold, while the embedding patterns decorate it. Let's see what happens when we start with the phrase, "a resting cat." Even if he hasn't seen this exact phrase before, Cliff has studied hundreds of millions of image caption pairs, so he knows what cats look like, and he also knows that resting can be used to describe something lying in a relaxed position. He generates an embedding for "a resting cat" that is very similar to the one for a cat lying on its side. To generate an image of a resting cat, we start with a point that is pure noise and therefore far from the manifold. We give this point to Una along with Cliff's embedding of the phrase, a resting cat. As Una moves the point toward the manifold, she tries to take it to a region whose decoration matches Cliff's embedding pattern. In doing so, she is selecting the region consisting of latent images of resting cats, or cats lying on their side. Once she has reached a point on the surface of the manifold, Vi will map that point to an actual cat image. Prologue to Act 5, Slices. To better understand the nature of the 4,000-dimensional manifold, we'll look at slices from it. But let's start with a simpler slicing exercise. Each of these contours is a two-dimensional manifold representing a family of latent cat images. We generated these 2D manifolds by taking slices of our more complex three-dimensional cat manifold. Depending on the directions along which we take our slices, we will get different families of 2D manifolds. We can slice the manifold in many possible directions. In fact, we're not limited to directions aligned with the coordinate axes. We can use any direction we like. And this provides for great variety in the slices we generate. These slices are families of cats lying on their side, while these slices are families of cat faces. Some slices are small ovals, while others are larger, more complex contours. Looking at all these 2D slices gives us some idea of the richness of the 3D cat manifold. Now let's see what we find when we take slices of the full 4,000-dimensional manifold. Act 5, Composition. Our 4,000-dimensional manifold is incredibly rich in information, more rich than you can imagine. One slice of the manifold yields our familiar submanifold of cats. Another slice yields a submanifold of trees, and so on for other objects. Recall in Act 2 where we showed a point slightly off the cat manifold, mapping to a cat that was slightly off. Why didn't it map to a noisy, regular cat? What happened was, we accidentally chose a point that was on the manifold, but on a different slice than the one we intended. This slice was a submanifold of strange-looking cats. Without the help of Cliff, Una does not know which slice to choose. Cliff's guidance helps Una choose the right slice. But here is where things get really interesting. Slices, or submanifolds, are not limited to single objects like cats or trees. We can have submanifolds describing different compositions of cats and trees. For example, there's a submanifold of cats sitting under trees, and one of cats sitting in trees, and one of cats made of trees, and one of trees made of cats. When we give Cliff a description such as a cat sitting under a tree, he combines the meanings of the words to get the meaning of the phrase and uses this meaning to construct an embedding designating the submanifold that Una should aim for. So we can think of Cliff's embedding as specifying a slice of the manifold, while Una maps noisy points onto the surface of that slice. And as always, Vi maps points on the surface to images. Although we've used 3D surfaces to visualize the submanifolds of cats and trees, we now understand that the real submanifolds exist in a much higher dimensional space. Sticking with our 3D visualizations, we can offer an artistic impression of the submanifold of trees made of cats. You can see that it's a complex surface containing both cat-like elements and tree-like elements. We conclude our exploration with 3 astonishing things about the computational artifact we've been examining. First, the full manifold contains infinite variety. Not just an infinite number of cats, an infinite number of trees, and an infinite number of other objects, but also an infinite number of ways these objects can relate to each other. Second, this manifold with an infinite variety of latent images was learned from examples. 400 million image caption pairs is a lot of examples, but it's not an infinite number. Using machine learning to construct complex mathematical functions, each realized as a neural network, is what allows us to get infinite variety from a finite set of examples. Finally, the actual 4,000-dimensional manifold does not physically exist anywhere. Its description is captured in the weights of the neural networks we've been studying, and we can use these neural networks to sample points from the manifold whenever we like. But we will never see the whole manifold. It exists only as a latent space. The neural networks giving rise to the manifold are our friends Cliff, Una, and Vi. Together they form the heart of the diffusion model. Now you understand how giving a prompt to a diffusion model can generate a variety of images. The ones shown are not the only types of images the model can generate. The possibilities are endless. And you can explore them yourself using any of these tools. Cats in Latent Space was made possible by grants from NEOM Company and the U.S. National Science Foundation.